Ini موضح يعني ريستوران.
يا ما يشرع
Kişi.
عشان
Kişi.
يشرع يشرع ga shi nan dai amma ba fara registration ba. Mutane nawa ne?
An shiga da yawa fa mutum 18.
18. Ana jin ku ko ku ya kunna mai.
Ya ce ba a yi. Achieving wannan video ba.
All right, welcome all. Can you hear me?
Sorry, I actually don't know what happened. Supposed to send the link for the invitation, and many have registered, but I don't know why I have to keep doing this. Okay. So we will start. Okay, so you can see my screen. Can you see my screen?
Yes, sir.
Yes, sir.
Okay. All right. So yesterday we started talking about per unit systems, and you were able to cover how we can use per unit systems. This is continuation of yesterday's class, transformer taps and voltage regulation. So you might have a transformer, okay? Let's say you have your transformer like this. Okay, this is the primary, this is the secondary. Let's say this is step down. Okay, so if you use the whole voltage across, okay, let's say this is 230 and this is 110, okay? So 230 volts to 110 volts. So if you are going to use the full secondary, you're going to get 110 as the output voltage, right? But then you can do some tapping, maybe pick in between, in the middle or something like that. Let's say you pick something like create another tap here so that now you have a new voltage from here to here. So if this is the full voltage, let's say this is VT, for example, okay? You do this so that at least you can leverage and utilize the same transformer to power different types of circuits, okay? So this one, maybe VT can be 60 volts, okay, V tapped. So that's the idea of tapping, which you can do on a transformer. So that's why we said initially we assume that the turns ratio is fixed, which is constant. Okay, for example, NP over NS will be, let's say, 0.1. If you are in a step up, if you are in a step down, it could be, let's say, 10, constant. But here you can do the tapping to make it a bit what we call flexible for yourself. Okay. So that's what they are saying. Distribution transformers, they can have series of taps in the winding to permit small changes in the turns ratio. Typically, transformers may have 4 taps in the nominal setting with a spacing of 2.5% of the full voltage. Okay, so adjustments of up to 5% is allowed. So from minus 5%, for example, up to plus 5%. In between, you have minus 2.5, 0, you have 5 and 2.5. Okay, so we have an example here that a transformer, a 500 kVA transformer, okay, the input is 13,200 volts, which is the primary, which is the high side. The secondary is 480 volts, which is the low voltage side. So this is a step down transformer. It has 4 taps, 2.5% on its primary winding. So the primary winding comes with 4 taps on it. So now the taps are here, 1, 2, 3, 4, for example. Okay, what are the transformer voltage ratios at each tap setting? So what can you do? At 5% plus positive, at positive 5%, it's like saying, okay, what the 5% of 13,200? Okay, you can do the calculation using your calculator. I think that should be around 13,200. That should be around 660, right? 660. We multiply by 2, we get what? So you add that to this, yeah, 660. If you add 660 to 13,200, add 660, you end up with what? 13,860. Okay, so that's why we have this 13,860. At the 2.5%, you can also do the same calculation, 13,000 times 2.5%. Okay, and that will give you around 330. So 330, if you add it to 13.2, so 13.2 plus 330, you get what? 13,530, right? 13,530. Okay, then you have the nominal rating, which is 13,200 minus 2.5 and minus 5%. Is that clear? Is that clear?
No, sir.
It's not clear?
No, sir.
Okay. Let me have a whiteboard. Okay. Okay, so this is what we are saying. We have transformer, okay, like this. Sorry. Okay, this is our transformer. And this is the secondary. We are saying the primary side is 13,200 volts, okay? While the secondary side, this is a step down, 480. So what I'm trying to say is when you have taps in a transformer, you could be able to have some additional cables. Instead of to say your transformer can only work when the input is 13,200, you can allow some flexibility in the rating of the transformer up to what we say 5%. For example, our transformer can have 2 tappings. So who is making noise? Mariam. Mariam, you are making noise. So what is this? Is like saying, okay, nominal voltage is 13,200, okay, volts. This is what the transformer in the primary, that's the rating. Let's say this is in the center, 13,200. But we can put some tapping, some wires, so that if you have 2 wires, one from here in the center, okay, and then you take the voltage now, you see that this transformer has different rating than the nominal when you take the whole end of the transformer windings. And this is what we are saying. In our case, this is 5% in the negative. This is 2.5%. This is 0%, which is the nominal. You have 2.5% in the positive and 5% in the positive. So 13,200, what is 5% of 13,200? You can use your calculator, right? And multiply this by 13,200. So if we are in percentage, we say this is 5/100, right? So this and this will go. So 5 times 132 is what? 660. Okay. So that means our transformer can support input voltages of 13,200 plus 660, which is 13,860 volts. So we can get this to be the primary. Similarly, from the opposite side, we have 13,200 minus 660, and that gave us that previous value of what? 12,000, I think 840, something like that. Okay, we can have also do the same for 2.5%, which is 2.5 divided by 100 times 13,200. And when you do this, you get 330 volts. You can add that to 13,200 plus 330 volts, and you will get what? 13,530 volts. So what I'm saying is, if I take the nominal, the ends of the transformer, I get what? 13,200. If I take it from a new tapping, which is far from the nominal, I end up with what? 13,860. And this one is 13,530. This is 13.2. This is 12,000, maybe 770. This is 12,360. Is that clear? Is that clear?
Yes, sir.
Yes,
Okay.
sir.
All right. So we use this tapping so that we can allow for variations. Okay, we can allow for some adjustments in the field so that we have some allowance, right? Some allowance if your voltages are varied. And this voltage variation is mostly due to load. Some load have what we call high line impedances, and for that reason, the voltage varies significantly. Okay, but normal loads, they normally have constant input voltage throughout. Okay, so keep this in mind. However, we have a special type of transformer that is called tap changing under load transformer, or you call it voltage regulator. So when you're talking about voltage regulator, is that you have a system that always look at what you have. Okay, the type of load you have. If this type of load is going to cause huge voltage drop, then maybe it will switch to another tapping to allow us to accommodate this extra load. Otherwise, it can stay in the nominal region. Okay, we have these self-adjusting transformers, and they are very common now in the modern power systems. We have also what we call the auto transformers. So we're going to learn about auto transformers, but I hope transformer tapping is clear before we go to the auto transformers. Is that clear?
Yes, sir.
Okay. So the thing with transformers is that if you have tappings, so you will have, let's say, this is the core, right? Like this. Let me see if I can draw. Okay, assuming this is the core. So we will have, let's say, a winding here. Okay, have another winding here in the primary. In the secondary, you have your windings like this. So what we are saying initially is we can connect this and this down one here. We get that let's say the nominal voltage. If we connect this and this, for example, we get a different voltage. This and this, we get a different voltage, and so on. So the thing is that this type of configuration is expensive, because then we have to keep on making windings and windings just to address, you know, a 5%. You have a special winding for 5%, for 2.5%. You know, all this, you have to create their own windings. This is not very economical. So what should we do? Easily is to say, okay, why don't we have an auto transformer? Okay, and this auto transformer allow us to be moving that top winding around or across. For example, when we have the initial, so many of you are still trying to join. Okay, so let's assume we have our transformer winding like this. Let's assume it is like this. We can now bring a wire and take from, let's say, the center and do something so that we now have some variation in the transformer. This thing can be done automatically. We have a transformer, okay? It has only one winding, and it can come up with different voltage levels, okay? Inside the transformer, same transformer, you can have the primary all on with the same one winding and the secondary. You don't have to have separate windings for primary and separate windings for secondary. So just one winding to take care of both the secondary winding and the primary winding, meaning sometimes the transformer can act as what, a step up, and sometimes the transformer can act as what, a step down. Okay, so simply just have one single winding. Let's see if this is our core. All right, so we'll have some winding somewhere wound round. Okay, when we want to do step up, we make sure we collect a lot of, most of this here, and then maybe just few. So this will do step down, so that this NS is NP is more than this NS. Okay, one single winding, but we took out. As you can see here, this is the primary side, and the whole of this is the secondary side. To use a different color. The whole of this is the secondary side. So you can see now the primary is not, doesn't have as much windings as what, as the secondary. So this is what, a step up, right? This is a step up configuration. Okay. We have another configuration where the primary is the one that has the highest number of turns, which is all of this. And then we pick from it a small portion to make the secondary side. So in this case, we have a step down transformer. Okay. Is that clear? Is that clear? Is that clear?
Yes, sir.
Okay. So since the transformer coils are physically connected, right? Since if you have just one single core and you have the windings, then you took out some tabs. Let's say call this primary, you know, and then this from here to here, the secondary. Then that means They are all connected together. Okay. So the voltage in the common winding where these two are sharing, in this case, which means, for example, if you have your transformer like this, okay, with windings all around the place, and we say this is the primary, the whole of it, and then the secondary is only this. So this part, this portion here that is being shared is called the common. Okay, this portion here, okay, it's called the common part, and the voltage across this is called the common voltage. So this part here is what? The common winding, and the voltage across it is the common voltage. The current that is going through this is the common current. Okay. Then now the voltage across the whole series connection, which is here, is what? The series winding or series voltage. Okay, series voltage. And the current also that is going through the whole thing is the series current. Okay. The voltage on the low voltage side is called the low voltage current, and then the voltage on the high voltage side is the high voltage current. Okay, so we have VLIL for the low voltage side, and then VHIH for the high voltage side. Okay, so in the case of auto transformers, remember what is our torque ratio for our normal transformer? A is NP over NS, right? But in our case now, the two of them are sharing the same coil, the same windings, and one of them is the biggest one compared to the other, which is why now we can say the turns ratio is equals to the common voltage divided by the series voltage, which is also equals to the common number of windings in the common part, and then divided by the total number of the series winding. So this is this. In the case of the current to NCIC equals to NSE ISE. The voltage in the in the low voltage side is always going to be equals to VC. And then the voltage in the high voltage side is going to be the series connection, right? VC plus VSE. On the other hand, the current in the low voltage side is the summation of IC plus ISE, and in the high voltage side is equals to ISE. All right. So this is for auto transformers, and the reason being that we have one single winding, and if we take some part, for example, in this case, this is a what? This is a step up. This is the low voltage side. This is the high voltage side. This is the primary. This is the secondary. So this is a step up transformer. Okay. So if this from here to here is the VC, then the voltage from here to here is the VSE. Okay. Is that clear? Is that clear?
Yes, sir.
Okay. So now, if you take these equations and try to make just move things around, you end up with the voltage in the low side divided by the voltage in the high side can be considered as the ratio in the common divided by the summation of the turns, number of windings in the common plus the series part. Okay, so this equation, keep it in your arsenal. Okay, for the current relationship, also similar, but You remember current is inversely proportional to the voltage in this regard. That's why you see that IL over IH equals to NC plus NSE over NC. Okay. So now that we know about the current and voltage in the power transformer, what of the apparent power, okay, in the auto transformer? Okay. So there is something to keep in mind, that not all the power traveling from the primary to the secondary winding of the auto transformer goes through the winding, and as a result of that, the auto transformer can handle much power than the conventional transformer with the same windings. So if you look at, let's say, a step-up auto transformer, we can take the apparent input and output powers to be S in. We are talking about step-up, right? So if it is step-up, the primary side is what? Which is the input, is the low voltage side, right? We are talking about step-up transformer. That's why we said the apparent power, S in, is nothing but what? The voltage in the low, because it's the low voltage side, multiplied by the current in the low voltage side. And that means at the output, which is the high voltage side, that is the secondary, the voltage multiplied by the current in the high voltage side is the same thing as the output voltage, output apparent power. For the case of auto transformer, it is actually easy to show that the input power and the output power are going to be the same. Because if you look at your previous equation, this one, IL equals to this, and we say SN equals to what? VL IL, and S out equals to what? VH IH. If you do some substitution, for example, for the case of IL, okay, equals to this, and you will realize that at the end of the day, the power input is supposed to be equals to the apparent power output, which makes a lot of sense. That's how it's supposed to be, ideally. Okay. And it's also equals to SIO, that is the input and output apparent powers of this auto transformer. So this means if you have an auto transformer, the power in the windings can be given as what? VSE, because that's the voltage at the high end, times what? ISE. And we can conclude this to be equals to SIO multiplied by NSE divided by NSE plus NC. If you take this and make, so that means this can go down here. So this is SW over SIO, right? And we can take the reciprocal of that, where SIO over SW is equals to NSE plus NC divided by NSE. Okay, and this last equation is what is called the apparent power rating and its advantage over a conventional transformer. Which means that if you have power in your auto transformer, some amount of it will pass through the windings, okay? And then the remaining will pass from the primary to the secondary without being coupled through the windings. So what we are saying is that the smaller the series winding, the greater the advantage. It's trying to join. Is that clear? Should I come again?
Yes, sir, come again.
Okay. So what are we trying to achieve here? Okay, we want to see, compared to conventional power, conventional transformer, is the auto transformer giving us, something better or not? So let's look at a simple expression here, and maybe let's try to draw. Okay, let me open a white blank. Okay, let me open a blank. Okay, so what we are saying that an auto transformer, okay, is a transformer that has, let's say, one single core, for example, and this core has windings, okay, on it. And we can leverage this winding to create either step up or step down. One single transformer to help us do that, okay? We can either get step up if we have the primary side to only take some portion of the whole winding, whereas the secondary side taking on the whole portion. This gives you a step up configuration. And this part here, as I said, is what? This is called the common part. Okay, this part from here to here, because if you look at it, it is common between the primary side and the secondary side. And the voltage in the common is called the VC. Voltage in the common, and the current going through it is also the IC. Whereas this part here, okay, this is called the series side, because you have like two different windings in series. Okay, the series side. So the voltage here, we call it VSE, and the current here is what? ISE. So if you remember, what is turns ratio? Turns ratio A is what? NP over NS. And the NP in this case for step up, what the NP here is this part, right? Which is VC, right? And what is the NS is what? VSE. This is the turns ratio. And this side here, since it's a step up, is the low voltage side. Whereas this side here is the what? High voltage side. Okay, so we can also say our A equals to VH, no, sorry, VL over VH. Okay, that's A. But remember also, VC divided let's use L, VL divided by VH is also equals to what? NL divided by NH. Or you can say this is what? NC divided by NC plus NSE. That's VH. This side is VH. This side is VH. Okay. Is that clear? Is this clear? Same thing with the I. IH over IL. Okay, it's similar because they are reciprocal. Yeah, it's what? NC over NC plus NSE. So now with this, you can also get apparent power, right? Power, remember S equals to what? IV, right? So power in the input, which is this side here, is what? VCIC, right? VCIC. So S in is nothing but VCIC, and S out, power at the output, is what? VHIH in the high end. Now we know what VH is. VH is what? Is equals to this side, which is the VC. We have this relation. So that's actually what we are doing. At the end of the day, your objective is to see, okay, there is even an example, and I think that will make it a lot more clear. If we have, for example, a 5 mega MV8 auto transformer that connects 100 kV system to a 138 kV system. So the input is 110. The output is what? 138. So this is a step up. This is a step up configuration. Okay. So, so this a 5 MVA auto transformer that connects 110 kV system to a 138 kV system will have a turns ratio, which means 100 is to 28. This such an auto transformer will actually have the following windings. So remember, we want to know what the power in the windings, which is SW. We know SIO is what? 5 MVE. Okay. We know in the series part is 100, is 28. Also 28, but this is 10, 110. So that means our power in the winding is what? 1.015 MVA. So for that reason, you can see that your auto transformer will have windings that are rated at slightly over 1 MVA instead of 5 MVA. Okay, and this makes it almost 5 times smaller, and it's always considerably considered as cheaper option than going for the conventional transformer. If you go for the conventional transformer to get a 5 MVA, you're going to have to spend a lot of money, because at this point you have a core that is really big. You have so many windings, one for primary, one for secondary. But the auto transformer is saying that we make your life a lot easy. Just get one core, have a winding, and just have some tappings, and you'll be able to get power. Although it is cheaper, but when it comes to construction, of course, it is going to be a little bit more complicated than the conventional one, where you have the primary and the secondary windings separate. You have to consider adding some insulation, right, on the smaller coil, just so that there will be no leakage as much from the primary to the secondary side. And that is also the disadvantage of an auto transformer, because the primary and the secondary are connected. There is a physical connection. So if this, because of that, you can say that property of a conventional transformer where we have electrical insulation, because in the case of conventional transformer, the primary side is insulated from the secondary side. So in between them, there is no connection at all. But in the case of this auto transformer, we have only one single winding. So that is not there. So this is cheaper, okay, to construct, because you don't use much wire, much cable. But this one gives you more benefit because of the insulation of primary and secondary. So this is very obvious. Of course, anything that requires more resources is going to require more money, right? So let's just quickly take a look at a very short example that we have 100 VA 120 by 12 transformer, also a step down. It will be connected to form a step up auto transformer. Okay. This initially is a step down, but they want to make it step up, where the primary voltage is going to be 120 volts. So what's going to be the secondary voltage and what will be the maximum power rating? Lastly, what will be the power rating advantage? So if we have our equations that we obtained previously, we know that the voltage at the high end is given by the NC plus NSE, or by NC. You can multiply it by the VL. Okay. So what we are saying is that the V at the secondary side is going to be equals to 132 volts. So if you at the input you put 120 volts, at the output at the secondary side you get what? 132 volts. This is a step up configuration. So that's what we are trying to find. That's what they are saying here. We know that this common side has 120. This series side has 12. Okay. So what's going to, and the voltage across the common is 120. What's going to be the voltage across the both, the summation of the two? And this gives us 132. And we also want to find the maximum series winding current, which is going to be the S max divided by VSE. VSE is the voltage here. Okay, so let's see. We know that this one is what? 100 VA. So 100. And then the voltage in this side is what? Is 12 volts, which is given here, 12 volts. Okay. That means the current going in through here, ISE, is equals to what? 8.33 amps. So if we know this is 8.33 amps, that means, okay, the apparent power that is going in the secondary side, VSIS, which equals to VHIH, is nothing but 132, the voltage here, 132, times the current that is going, because ISE is the same thing as the IH. Remember, if you are in a series configuration, a single current of the same value goes through the whole circuit. Therefore, if this part here, ISE, is found out to be 8.33, that means the I in the high voltage side is also 8.33. If we know the voltage in the high voltage side to be 132, then multiplying the two of them, you will give you 110 VA. Okay. So the power rating is nothing but SIO, which is this one, divided by SW, which is 100, and this gives us 11. This you can also find it in a different way. If you use this equation here that we have found previously, where NSE plus NCO by NSE is what? The power rating advantage, which is going to give you 11. Okay, is that clear? So it's not that complex. All you have to understand is that in an auto transformer, you have some few equations, and these equations are easier to find, considering that this transformer has a single coil and this transformer comes with a tapping. The tapping will make the common side and the series side. And in the common side, you have a current and a voltage. Same thing in the series side, you have a current and a voltage. In the high voltage side, you have a current and a voltage. And in the low voltage side, you also have a current and a voltage. If you keep that principle of turns ratio, where A equals to NP over NS, all the other equations will fall into place. Okay, is that clear? Is that clear? We're going to do some simulation, so question, guys. Okay, so I guess it's clear. If you go to the store, electronics store, okay, and you ask them to give you power or auto transformers, you will see something like this, okay? You can see this knob. You can use this to regulate and set the tappings, okay, in your transformer. So you can have like both the step up and the step down settings using this. Same thing with this. This one has some knobs. You can pick the one that you want to get the value you want. Okay. So let's do the simulations. Is it clear? Guys, is this confusing or is it clear? Okay, I know many of you joined very late, so you are not even sure what we are trying to achieve, right? So if you join late, try to make sure you watch the video before the next session. Okay? Read the note, watch the video. Okay, let's go to Spider. So let's look at the exercise, okay? This should be easy. Okay, can you see my screen?
Yes, sir.
Okay. So we have a transformer. Okay, it is rated what? 10 kVA. The primary side is 480, the secondary side is 120, 60 Hz. Calculate the base values for voltage, current, and impedance in both the primary and the secondary windings. So first of all, what is the base values here? What is S base and V base? What is S base? What's S base? We discussed this yesterday. Per unit system. Are you guys revising your notes or you dump them after the class? So maybe next week we will have a quiz, right? I think it is high time. We will finish transformers next week, and then we will have a quiz on Thursday, same time. We're going to cover all of transformers in the quiz. So yeah. So this week we will have an assignment. Next week we will have a quiz. So tell your class members that next week there is going to be a quiz on transformers. So everything we've learned so far on transformers, there is going to be a quiz, and it's going to be on the application. I keep forgetting to send you the demo on how to register on the app. I will make sure I do so, okay, by the end of the week. I couldn't get the time to record my screen and explain the app. So the S base is 10 kVA. We discussed this yesterday, that the power doesn't change throughout. And the V base, you can take it to be 480 volts. Okay. So we have the S base, we have the V base. And based on that, you can go ahead and calculate the per unit values. Okay. We have the next one is saying that simulate the voltage regulation of a transformer under different power factor conditions. We did this yesterday. Under lagging, unity, and leading. And we were able to see if it is lagging, then the voltage regulation is going to be greater than 0. If it is unity, and if it is leading, we also saw that the voltage regulation value is going to be less than 0. We have some values for our transformers. The V nominal is 230 volts. The P rated is 15 kVA, and the Z equivalent is 4.45 plus J 6.45. Okay, so we want you to do two things. One, simulate the transformer in the per unit system. The second one is to get the voltage regulation. And then we want to see what is going to be this voltage regulation if we have a lagging power factor, a unity power factor, and a leading power factor. We want to plot this, okay, as a function of the load current. We did this yesterday. We also want to calculate the efficiency of the transformer at full load with a full power factor of 0.8. Okay, if the power factor is 0.8, what's going to be the efficiency? We also did this yesterday. So in code, now that's what we want to see how it works in code. Okay, before we move to code, let me know, is this clear? What is expected? Is it clear what is expected of you or no? Okay. I will assume you are not revising your notes, because if you are, there shouldn't be a problem. So let's run the code and then I can explain what's going on. So here, I don't have to explain these two lines. They should be obvious and clear to you. We set the nominal voltage to 230, the P rated to be 15 kVA. Z equivalent is set to 4.45 plus 6.45 J. We did this calculation yesterday that the I rated is what? The P rated divided by the V norm. So for different power factors, 0.8, 1.0, and 0.8, we can find the thetas, right? Thetas accordingly. So what do you do to find theta? Cos inverse of 0.8 was that, cos inverse of 1, cos inverse of 0.8. When you get that, you can find the V full load, right? And then based on that, we have also this equation. We said V full load is nothing but V norm using Kirchhoff's second law, right? Then Kirchhoff's second law. So that's how we were able to find the V full load. And we are now using this library, matplot library, to plot. We are plotting to see what happens. So at lagging, this is it. At V norm, at unity, we are at what, 230, and this one. So this one in phasor form is kind of saying this is 210. The angle between this and this side here, okay, the angle here, I think is around 60 degrees. You can try it. Cos inverse of 0.8. I think it could be around 60 to 70. And then cos inverse of 0.8 also. So here is like minus 70 degrees. Okay. Is that clear?
Yes, sir.
Yeah, the code is easy and is self-explanatory. So I'm going back now to look at the next simulation. Let's discuss it also.
So please, can you send the code?
Yeah, I will share the code.
Okay.
I will send the code. I always send the code, right?
Yes.
So you can go and play around with the values to see what you get it. So next is we want to see the transformer tap simulation. As we discussed, you can have a single transformer, right? And then you have the primary and the secondary coil. But in the primary or in the secondary, you can have some taps that will give you some variation, maybe 5% more than the nominal voltage, 2.5%, or minus 5% or minus 2.5%. Okay, so assuming your nominal voltage is 13,200 and your transformer has 4 taps, 5%, 2.5, the nominal, of course, minus 2.5 and minus 5%. We want to simulate and plot the primary voltage at each tap setting. So what is the tap setting? When it is at nominal, it's 13.2. At 5%, we did this calculation, it's what, 13,860. At 2.5%, it is what, 13,530. Same thing with minus 2.5 and 5%. So we want to plot the primary voltage, okay? And there are some questions here for you. One is to explain the purpose of using taps in voltage regulation. Why do we use it? And how the tap settings adjust the voltage. Okay. Another thing is how does the adjusting the tap setting help in maintaining a stable voltage when load or input voltage fluctuates? This is something we've discussed. So you can expect a question like this in your quiz, for example, okay? So this is like giving you a sheet of how I frame my questions. Okay, so next is I will share the code, but it's clear what is expected of you. Okay, can you see my screen? Can you see the code?
Yes, sir.
Okay, so here we have the transformer parameters. We know our V norm, we know our percentages for the tabs, and we know the V secondary, right? So we can find the V tabs using this simple, I don't know, you know, list comprehension in Python. I'm sure they must have taught you that. So let's run this code. So this is the voltages, right? V norm is the one, 13,200. You can see it's here. When you increase by 2.5%, you can get up to what, 13,530. And then if you increase up to 5%, you get 13,860. Okay. So is that clear? At least this gives you a visualization of the ranges of values your voltage can be able to see. So we can maybe change the value of the V norm, let's say for 80 volts. Let's see what happens. And the V secondary, let's put 240. Okay. So now it has changed. 480 is the nominal. When we make 2.5% adjustment, we get around 492. And we get around 508 and so on. Is that clear?
Yes, sir.
Okay, so let's look at the next, which is the last one, simulating an auto transformer. So you want to simulate an auto transformer. You have some parameters. One, that the common winding, which we discussed, is 120, and the series winding voltage is what, 12 volts. If the turns ratio, NC divided by NSE is what, 10:2. Okay, so we want to see what this is going to be. And these are some questions: simulate and plot the voltage and current in the auto transformer. Okay, and explain the relationship between the common and series windings. Calculate and plot the apparent power advantage of the auto transformer over a conventional transformer. Okay, is that clear?
Yes, sir.
Okay, so let's move to the code. Okay, let's run this. Okay, so we know our VC, we know our VSE, we know our NC, we know our NSE. These are given from the question, right? And we know that VH, the high voltage side of the auto transformer, is given by VC plus VSE, okay, times NC over NSE. This will give you VH. And what is VH? 180 volts. Okay. Then we also go ahead to find the IC, which is the current that is going through the common winding. The common winding, the part that is shared between the primary and the secondary. Okay, and assuming it is 8.33, then the I in the high voltage side is what? The ISE, right? The ISE. And to find the ISE, you can use this equation, the voltage in the current in the common divided by the voltage in the high voltage side, which we already obtained from line 16. So that gives us what? IH, which is the auto transformer current, which is 5.5 amps, 5 amps. Okay. If you are dealing with, you might want to print it out. So we are trying to plot here. We have VC and VH. Okay. VC is the one in the common, and VH is the in the high voltage side. So of course this is 120 and this one is what? 180 as we obtained. You can use the bar chart to plot it to make more sense to you. A picture speaks louder than words. Here we have the current also. You can plot it in the bar chart to see that the IC is far more than the IH. You can play around with these values to see how these things are going to keep changing. So all these codes are going to be forming a basis for your final transformer design project, which you're going to do. So basically, I'm giving you some snippets of the code that at the end of the day, you're going to put all together. It will help you to design a full transformer, simulate it before you go and construct. Okay. The reason why we always simulate before construction is because it is cheaper to simulate than to construct. It's cheaper, it's easier. If you have to construct a transformer, it will take you some time. If you make a mistake in the number of windings, it's going to take you a lot of time to undo that mistake. But if you are simulating and you try a certain value, let's say for the V common, and it is not giving you the output you are expecting, the VH, you can play around with the V common until you get the right value that you require. Once you get the right value you require, you know the value now that you're going to do. You know the number of turns you need to wind in the primary or in the common, and you know the number of windings you need to put in the series. So that's the advantage of having simulation. At least when you get a simulation, you can play around with the values to make sure you get the output that you desire. And once you get it, then you can go ahead and play and construct. Okay. Is that clear?
Yes, sir.
Question? Do you have any question?
Sir, I have a question.
Okay, what's your question?
I think sometime in the line. Please, what's the difference between the auto transformer and the normal transformer?
The difference between auto. Okay.
Yes.
So the conventional transformer has two separate windings, primary and secondary, and there is an insulation between them, meaning there is no connection between the windings in the primary and the windings in the secondary. Is that clear? You know this conventional transformer has two windings, right? Primary winding and secondary winding.
Yes.
No connection between the two. Each one is
Yes.
isolated.
Yes.
For auto transformer, you have one single winding. Okay?
Okay. Yes, I understand.
Clear?
Yes.
You have one
Yes,
winding, out of which you take out some taps. Okay, you take out some taps. Okay,
sir.
the tap you attach to the input becomes the primary side, and the part you attach to the output becomes the secondary side. Okay,
Yes,
so
sir.
this is a single winding. Everything is connected. So for that reason, the auto transformer is cheaper to build and construct than the conventional transformer.
It's clear,
Is
sir.
that clear?
Yes, sir.
Any other question? No question? Okay. So I will try to see that I send you. Okay, I will try to see that I send you a video for how to use the app, and I will put some quizzes on the previous section on the previous session. Okay, I'll put some quizzes for each of the previous lessons that can serve as practice quizzes for you. Is that clear? Against the general quiz that is going to take place on Thursday. All right. So starting from lecture 1, I will put the material there, the lecture note, and then there will be like 10 questions, multiple choice, fill in the blank and essay. Lecture 2 up to the last lecture, which will be, I think, this is 7, so lecture 9 or lecture 8 will be the last one. So you are going to have some practice tests. Go and do all those quizzes. All those ones I'm not gonna grade, but it is for your own sake. Okay.
So about the quiz,
yeah,
is it going to be online, like on this platform, this same
it's going to
platform?
be digital, yes.
Okay.
And it's going to be random. So each one of you will have different sets of questions. Okay. Each one of you will have different sets of questions. The same difficulty level, of course, just like JAM.
Okay.
So if you want to copy from your friend, please, you go ahead and do so. Yeah. So go ahead and copy from your friend, no problem.
Sir, I have a question, sir.
Yeah.
What is based on the transformer simulation assignment?
It's going to be based on the transformers.
No,
it could be based on the simulation as well as the theory.
So my question is based on the transformer assignment you sent to the group.
Okay, the last one I sent.
Yes, sir.
Okay.
Yes. The first part is asking us to calculate the current in the primary and secondary winding of the transformer.
Okay.
But the parameters given to us are the primary voltage, the turn and the turn ratio.
Okay.
That's only the parameters given to us. So even if we can calculate the secondary voltage, I don't know if it's possible with those parameters to calculate the primary current and the secondary current.
Do you have the rating of the transformer?
No, there was no rating on the transformer.
No VA?
No.
Okay, I will check the question again, but it should be straightforward.
Okay, sir.
Maybe during typing, I forget to add some parameter. I will check.
Okay, sir. Thank you.
Problem. Okay, guys. In the absence of any question, I will have to say see you next week. You will receive your next assignment. You will also get the quizzes for you to practice against the exam on Thursday. Okay? Thank you. Have a good one. Enjoy your weekend.